Welcome everyone. In this video lecture, we will cover operation with a differential input voltage in a MOS differential pair. In last video lecture, we have covered the MOS differential pair with common mode input voltage. So today we will cover MOS differential amplifier operation with differential input. Okay. So in this one, we will try to cover the differential input, okay, voltage in a MOS differential pair. So we will start with the fundamental MOS differential pair, which consists of two transistor. MOS transistor, say I am saying this one is M1 and M2, okay, in which we are giving the voltage, differential voltage, say VID, through the gate of gate terminal G1, and we are taking output across this one D1, the drain terminal D1, and this one is our source S1. So and this terminal is our D2, and the gate of the second terminal of the MOS is connected to ground, and this one is our source of S2. Okay, so this one is the circuit. Here the VDD supply for the both the resistance RD, and there is a differential voltage VID, and the common current source here, which is connected to the both the source end of transistor M1 and M2, is our I with a power supply minus VSS. Okay, so we are discussing with the differential input voltage. So here what we observe, that the differential input voltage, that is our VID, the differential or input voltage, this one is our VID, can be observed by grounding the gate terminal. The gate terminal we are just grounding. Okay, we are grounding the gate terminal G2. Okay, we are grounding the gate terminal, okay, of Q2, that is our VG2, is simply our 0. Okay, that is our VG2. Okay, that is our VG2 is 0. Okay, so that we have already written here. Further, and applying a signal VID to the gate of the Q1. So this one is the gate of the Q1. Okay, so through that gate of the Q1, we are applying a voltage, that is our VG1, is nothing but simply our VID. Okay, VID, that we have. Okay, so this statement is clear. Differential input voltage VID can be observed by grounding the gate terminal, of M2 transistor. Okay, and giving the differential voltage VID across the gate 1 of the transistor Q1. Okay, so you can also write Q1 here. I have already written Q1, Q2, so better to make it Q1. Okay, make it Q1. Okay, Q1 and Q2 transistor. Q1, Q2 transistor. Okay, so this, and applying a signal VID to the gate of Q1, that is our VG1 is VID, and gate of G2 will be grounded. So we are just putting this one as a 0. Okay, so next circuit is clear. Next, again the same circuit we have made. This one is our Q1 transistor, Q2 transistor, and this voltage is nothing but simply get to source voltage GS1 and VGS2. So the differential voltage, we can say the VID value can be written as VGS1 minus VGS2. Okay, this can be also obtained by just applying Kirchhoff's voltage law in this section. If we apply Kirchhoff's voltage law in this section, what we can write, plus VID minus VGS1, then plus VGS2 equals to 0. So the VID value will be simply VGS1 minus VGS2, that I have already written. Is it okay? Is this line is okay? So this one is the VID, the differential voltage will be get to source voltage of this one minus this one. So this can be easily obtained by using Kirchhoff's voltage law in this loop. Okay. So VID is positive means if I am saying the differential input voltage is positive means get to source voltage will be always greater than VGS2 means if I am saying VID is a positive value. Okay. So it means VGS1 is greater than VGS2. Okay, so the same statement is written here. When VID is positive, okay, VID is positive, this VGS1 is greater than VGS2. So VGS1 will be greater than VGS2. And if VGS1 is greater than VGS2, the current in the ID1, okay, because now what we observe that VGS1 is greater than VGS2. Okay, so the current ID1 is also greater than ID2. Okay, because the current expression, the drain current, we can write 1 by 2 K and S W by L VGS minus VT whole square. So now for the transistor 1, so VGS1, if this one is greater, then ID1 will be greater than ID2 because ID2 in ID2 the VGS2 value is lesser. So ID1 will be always greater than ID2. So that is statement we have written here. And this all are from the microelectronic circuits book by Cedar Smith. So ID1 will be greater than ID2. So is it clear? ID2 because the get to source voltage that is our VGS1 is greater than VGS2. Okay. For VID positive. For VID positive. Okay, because VID equals to VGS1 minus VGS2. So now the difference, the VD2 minus VD1 will be positive because now the voltage drop, the VD2 can be written as VDD minus ID2 RD. Okay, this VD2 is just simply our VDD minus ID2 into RD, and in this case it should be VDD minus this current ID1 into RD. So now this ID1 current is higher. Okay, this ID1 current is higher. Okay, so this value will be smaller, and in this case ID2 will be what? ID1 will be larger, so this value will be smaller, and this ID2 is smaller, then this value will be higher. Okay, so VD2 will be always greater than VD1. The voltage across the drain terminal of D2 will be greater than VD1. Is it okay? So the difference of output voltage will be positive. That is our VD2 minus VD1 will be positive value because ID will be less. Okay, so overall voltage drop will be less in case of VD2. So VD2 will be greater than VD1. Okay. Is it okay? Simple. On the other hand, when VID is negative and when we are saying VID is negative, the gate to source voltage will be lower than VGS2. Means our VID, I am writing here. Okay, I am selecting some different color. VID equals to VGS1 minus VGS2. We have observed. And now I am saying this VID is a negative value. Negative value. So we can simply say the VGS2 is greater than VGS1. Is it okay? VGS2 is greater than VGS1. So on the other hand, when VID is negative, VGS1 will be lower than VGS2. Simple. Okay. We know this expression. Then we can say, I am highlighting this one. Is it okay? Now, similarly, the ID1 will be smaller because the value will be ID1 will be smaller than ID2 and correspondingly the VD1 is now become higher because in this case get to source voltage will be high. So current will be also high, so id2 will be id2 will be, in this case it is larger. Id2 is greater than id1 when we are considering the negative one. Okay, the vid value is negative, so id1 will be smaller than id2, and correspondingly vd1. So if id2 is higher, so vd2 will be what, smaller than vd1. Hence the differential voltage vd2 minus vd1 will be negative here. In this case vd2 minus vd1 will be negative. Very simple. You can also follow the microelectronic circuits book for more detail. Okay, so this part is clear. Okay, next. Now differential pair corresponds to differential mode input signal by providing a corresponding differential output signal between the two drains. Okay, means differential pair responds to differential mode input signal corresponds to differential output signal between the two drains. At this point, it is useful to inquire that the value of VID that causes the entire bias current I. Okay, the value of VID which entirely gives the bias current I to flow in any one of the transistor. Okay, at this point we will try to analyze the value of VID that causes the entire bias current I which will flow in one of the two transistor, either from Q1 or Q2, either from Q1 or Q2. The current I, the bias current I, either it will flow from Q1 or Q2. Okay, here means this bias current I, either it will flow from this, then it should be 0. If it will flow from this side, it will, this current will be 0. Okay, clear this one? So it is very simple. For more detail, you can also follow the Sedra Smith book. Okay, clear. So for the positive direction, okay, when get to source voltage is positive, this happens when VGS1 reaches the value that the corresponding current ID1 equals to I. Okay, ID1 is I, and VGS2 is reduced to a value equal to the threshold voltage minus VT. Okay, because VGS 2 we can write as get 2 minus vs2. Okay, get is grounded and vs2. Okay, so the current will be 0, so we can write vgs2 minus vt. If it is 0, we can say, so source voltage if we make it to minus vt. Okay, because this will be minus vt, so it should be cancel out. Okay, so see, so now what we will do, ID value will be I. Okay, we have to flow the current through transistor Q1. Okay, Q1. So what we can write, I equals to 1 by 2 K N dash W by L VGS minus VT whole square. Now, so I value will be twice I, sorry, we can write like twice I K N dash W by L VGS minus VT whole square. And this value is nothing but simply the overdrive voltage, and it is just the square root of twice I by K n dash W by L. Okay, then VGS1 we can write as VT plus this, and this one we can write root 2 and VOV. Okay, overdrive voltage. In last video lecture, we have already defined the overdrive voltage will be a square root of I by K n dash W by L. Okay, for the current I by 2, for the drain current I by 2. So VGS can be written as VT plus root 2 VOV, and VOV is the same square root I divided by K and dash W by L, where VOV is the overdrive voltage corresponding to a drain current of I by 2, corresponding to a drain current of I by 2. It is important to note that this one, for I by 2 current, the overdrive voltage will be this. Okay, so this will be the expression for get to source voltage. Okay, vt plus root 2 vov. Okay, now Thus, the value of VID at which the entire bias current I is steered into the Q1 is okay. So, what we can do means the all the current we are saying the current is going from this the due to this differential voltage, and this current is zero. Okay, so already we have discussed the maximum value of this voltage VID max equals to VGS1 plus Vs, and this one will be just Vt plus root 2 of VOV that we have find just above VGS1, and plus Vs. This Vs we have already find. We have to make this as a minus Vt. So the maximum value will be root 2 VOV. Okay. Now see, from here also you can find the value. Like VID max. So VID max minus VGS1 minus plus VGS2. Is it okay? This line. Just Kirchhoff's voltage law in this loop we have applied. Okay. Then VID max VGS1 minus VGS2. Now VGS1 value we have already calculated like VT plus root, and VGS2 can be written as VG2 minus VGS2. Now VG2 is grounded. VG2 we can say grounded because the get terminal of 2 is grounded, and VH2 is nothing but simply plus VH2 minus minus plus VH2. And when initially we have mentioned that the when VH2 equals to VT minus VT, it is 0 because the current we have to make this current will be 0. So the expression of the current will be what? K and S by 2 W by L VGS2 minus VT whole square. Okay, so VG2 is 0 and this value will be K and S by 2. Okay, I am Vg2 minus Vh2 minus Vt equals to 0. So this Vh2, if we make it minus Vt, okay, minus minus plus, so this should be cancelled and Vg2 is grounded, so its value will be 0. So Vh2 value will be minus Vt, okay. So the value become root 2 times of VOV. So maximum value will be root 2 times of VOV. So if VID is increased beyond root 2 VOV, okay, when the differential voltage VID is increased beyond root 2 VOV, ID1 remains equals to the current same as that of the bias current I, and VGS1 will be equals to VT plus root 2 VOV, and it rises correspondingly, thus keeping the transistor Q2 in the off state. Okay, simple calculation is there and simple concept. A similar procedure is can be obtained for the negative direction when VID becomes minus root 2 VOV and Q1 turns off and Q2 conducts for the entire bias current. Okay. Hence, we can say the current I can be steered from one transistor to the another by varying VID in the range in between root minus root 2 VOV to plus root 2 VOB. So this one is a very important observation. So I am highlighting this one. This one will be the important observation, means it should be vary from VID value. In case of differential one, it will vary from minus root 2 VOV to root 2 VOV, which defines the range of differential mode operation. So this is all about the differential most differential operation due to the differential input voltage. So differential input voltage then comes between minus root 2 VOV to root 2 VOV. Okay. Now the summary. So summary, most differential pair operation with differential input voltage then. So VID lie between root 2 VOV to plus root 2 VOV, and get to source voltage if you find it will come VT plus root 2 VOV, and this VOV is nothing but simply overdrive voltage corresponding to a drain current I by 2, and the maximum value root 2 VOV we have already covered, and the same thing we have written in the description for this. In the positive direction, this happens when VGS is the value that correspond to ID1 I, and VGS is reduced to a value equal to the threshold voltage VT at each point. Vs equals to minus VT at this point. So Q1 is on, Q2 is on, Vs2 is minus VT. Then drain current equation if you write, we will get Vt plus root 2 VOV, where VOV is I by K and dash W by N. Similarly, for the maximum value, it will come root 2 OV, root 2 VOV, and in the negative direction, VID minimum will be minus root 2 VOV, where Q1 will be off and Q2 will be on. And VOV is nothing but simply the overdrive voltage corresponding to a drain current of I by 2. So that we have to keep in our mind. So this is all about the most differential pair operation with a differential input voltage VID. So this is all about this lecture. So please follow this lecture. If you are getting some difficulty, you just try to finish the first part, okay, with common mode input. And for more detail, you can also follow the microelectronic circuits book by Cedra Smith. So thank you for watching this video. Thank you.